I would like to welcome you all, respected members of the PhD committee, to my PhD presentation. And today I'm going to talk about all the projects that I have done during my PhD. You received my thesis, and in it I am describing only one project in my PhD and mentioning only two of them just as a mention. And today I'm going to talk about all the things that I have done. So the title of my thesis is 3D multi-channel convolutional neural network for prostate classification. And today I'm going to talk about everything that I have done during my PhD, which is neural networks for prostate zone segmentations and cancer classification. I'm Nader Aldoj, supervised by Mark Device, Sebastian Stoba, and Tobias Schafter under BioKick program. So in the agenda of today, I'm going to talk about 4 projects. Project number 1, classification. Project number 2 is segmentation on T2. Project number 3 is about MR elastography of the prostate. And project number 3 is segmentation on MR elastography images and also the thesis. Everything in my presentation is going to be color-coded, so it's easier for you to follow. The timeline of my PhD, I started around mid-2017, and the first paper was published around August 2019, and I wrote my thesis at this time point, this time period here. That's why I only included the content of this paper and didn't include any of this and this, only just a mention, just because this paper was accepted at the last stage of me writing a thesis, so there was no enough time for me to include everything in it. Just to give you a brief example. And the last paper here, it's about MR elastography segmentation, and this paper, the first paper was published, the second paper is published, the third is published, and this one is submitted to scientific reports. So before we begin with the presentation, just me clarify some terms. So first of all, what is a neural network? Whenever you hear me say a neural network, it's just an algorithm that take an image and perform some mathematical operation on it so that it can come up with a prediction such as this is tissue is cancer or no cancer, or maybe also segmentation, or this pixel belong to this one, this pixel belong to the tumor, this pixel doesn't belong to the tumor, and so on. In order to train that, we have to introduce a term called loss function, which is telling the network if it has done a good job or a bad job and how to correct for the bad job and to keep proceeding and improving throughout the training process. And since we all know that the data, image data is scarce, so we need some sort of a way to augment our data so that we increase the generalizability of this neural network by doing some data augmentation, by deforming the images in a way that they look like a new images, but they are not. So just like a synthetic kind of images, with just doing some deformation on the images themselves, just to clarify those terms. Now let's begin with the work that we have done. So we used datasets because our algorithms need dataset to learn from, and in this job we use 2 datasets, so Prostate X dataset and Charite dataset. Prostate X dataset is 204 patients, Charite MRE dataset is only 40 patients. For the Prostate X, we used it in the project number 1, which is a classification of prostate lesions, and project number 2, which is segmentation on T2 images. For the Charite MRE dataset, we used it for project number 3, which is in vivo quantification of water diffusion on prostate cancer and BPH, and for project number 4 also, which is segmentation on the MRE and MRI dataset. Any kind of project needs some sort of pre-processing and data augmentation for the data to be eligible to be used in during training this algorithm. And such pre-processing could be cropping the big and large volumes to smaller volumes, and also some data augmentation, so playing around with brightness, darkening, sharpening, translation, rotation, and so on. Could be also non-rigid augmentation or non-rigid pre-processing, such as deforming the image in such a way that it looks like a new image. and also this been used in project number 2 and number 3. Let's jump to the project number 1 and discuss a little bit more. So the idea behind project number 1 is prostate classification of prostate cancer classification. So we have such images of different sequences of MRI, so multiparametric MRI images, and then we need sort of a network so that it can be trained on those images and spit out the desired classification, whether this lesion is cancer or no cancer, or clinically significant or clinically non-significant. And in order to do that, we designed this type of architecture. It's taken 3D volumes and it's processing the volume, and it's coming out to the final decision whether it's cancer or no cancer. And we have also studied the different sequences and the combination of different sequences and the effect of different sequences to the overall performance by applying those sequences and letting the network learns from those sequences and monitor the performance. And here in the first round, we used all the sequences as input to the network. Here we eliminated the T2 to understand how the T2 will affect the decision. Then we eliminated K-trans, and then we eliminated also the ADC and DWI in the final try. And the results, we found out that this is the best combination of sequences that can give us the best performance of the network. And also we found out that K-trans carries the most useful information about tumor characteristics in this data set in specific. If we take a look also at some examples here, we can see the statistical categories: true positive, false negative, true negatives. We can maybe tell from those images that maybe the larger the lesion is, the better the diagnosis. But when we studied this numerically by plotting the mean and the median of the lesion size and the lesion largest diameter, we found that there is no actual difference in terms of performance when it comes to larger or smaller lesions. And here are some examples of wrongly predicted lesions. Only those two wrongly predicted. This one is right predicted, but it's just like some misclassified lesions, whether they are non-significant and they were classified as significant, and significant classified as non-significant. Just telling you that the performance of the network is not ideal, is not like 100%. It's just comparable to the human radiologist. If we jump to the prostate zone segmentation, which is project number 2, let's formulate the problem. We have a bunch of images and we have these masks, and then we have to come up with an algorithm or a neural network so that this algorithm will help us on fully automatically segmenting the prostate and the underlying zones of the prostate. And in this project, we designed a new architecture of a network that's called dense UNet. It's based on the state-of-the-art UNet, which has this shape of U. And then we introduce a concept of densely connected layers, densely connected convolutional layers, as you can see here, to make the product, or to make this unit is more compact, more compressed, and more efficient in terms of parameters and performance, hopefully. And we tested this network against many aspects. So the first aspect that we have tackled is the quality of the ground truth, whether the quality of the ground truth will affect the performance of the network or not. Then we tested it against other state-of-the-art methods. We tested it with four-fold cross-validation, and then with different type of augmentations, of data augmentation, and finally different loss functions. As you have seen, loss functions will affect also the performance of the network. And let's dive deeper into those details. As you can see here, this is the effect of ground truth. And as you can see here, the radiologist was lazy on finding out the exact borders of the prostate here and there, of the zones of the prostate, while the network actually learned to find the exact borders, or roughly better borders, of the prostate than the actual ground truth. So even if the ground truth was bad or was not accurate enough, the dense unit was able to find out where the actual borders are, and in comparison to the classical unit was much better in classifying the or finding out where the prostate is and give us good segmentations. If we jump to the test of the dense unit against other state-of-the-art method, we have the classical unit that we are testing against, and we've taken it as a benchmark. We have also cascaded unit and the PSB unit. Those are state-of-the-art methods in this realm. And as you can see here, just images, examples of the segmentations. And as you can see here, also in comparison to the other state-of-the-art unit, state-of-the-art nets, our dense unit was better in all segmentations, whether it's for prostate, peripheral zone, or central zone or transitional zone. For the four-fold cross-validation, as you can see, cross-validation looks something like this. We just split out the training data into training and testing, and we shuffle and we do the splitting again and again. And as you can see here, all the folds were not actually significantly better. The dense unit was slightly better, but what is not significantly better, except for this fold, where the dense unit was significantly better in terms of segmentation. And this is due to the fact that just by chance, the test set here was containing some special cases that could be like a BPH grows into the bladder. As you can see, the classical unit was wrong in segmenting this tissue in the bladder, since BPH grows into the bladder, while the dense unit was accurate in segmenting this. Also here in terms of TURB, the classical unit was wrong about segmenting the whole thing as prostate, while the dense unit was more accurate in segmenting only the prostatic tissue. Here it was a big tumor. The classical unit did not care about the tumor and consider it as not prostate, while the dense unit was accurately segmenting the prostate and the tumor of the prostate as a prostate tissue. And if we jump to the different augmentation types, we have here different augmentation types, and rigid augmentation types here and non-rigid augmentation types here. And we can see that then the dense unit was not, the performance of the dense unit was not so different when it comes to different kind of augmentation. If we test the last point, which is the loss function, we have used many loss functions, something called a cross entropy loss function, something called focal loss function, which is downweight the easy examples and focus on more examples. So it's just a slight modification of the cross entropy. Cross entropy is just comparing the pixels toward each other. So the pixel of the predictions of the network and also the ground truth that come from the radiologist. And this is just a better version of the cross entropy, and also the DICE score, which is measuring and maximizing the overlap in between the predictions and the ground truth. And we can see that there is slight difference, but not significant difference in the performance. So again, this is not significantly affecting the performance of the network. If we jump to the project number 3, which is in vivo quantification, in vivo quantification of water diffusion, stiffness, and tissue fluidity in BPH and prostate cancer. Here is the images of the BPH. Here is the images of the prostate cancer. And as you can see in the table here, there is an increase in the values of shear wave speed and loss angle, but there's a decreased value in the ADC, which indicates stiffer tissue properties of the prostate cancer in comparison to BPH, reduced water diffusion, and increased tissue fluidity, which actually correlate with the known already published results, which increased cell density and fibrous protein accumulation. I didn't go deeper into this project because this is the only part that I have participated into the project, so I was only a co-author in this paper, but not the first author. Now let's jump to the final project, which is prostate zone segmentation using MRE and MRI dataset. As you can see here, those are MRE images and those are MRI images. So MRE means MR elastography. We have magnitude map, we have C map or shear wave speed map, and then we have the phi map, which is the loss angle. And then we have here in the MRI T2, DWI, and ADC. And the idea is to come up with a network that can actually segment the prostate into its zones, so a peripheral zone and central zone, or you want to call it a transitional zone. And here, how did we handle the data? Because we have so many different combinations of input that we can think of, we actually thought of every single combination of the data that you can think of among the MRE or the MRI sequences. So here all MRE and all combination of different kind of things that we that might come together, and we trained specific model for each of those combinations, and then we have the output for each single combination. We call this individual models. And then we have another approach, with the approach letter B, which is the unified model, where we considered all different combinations and we put them in one data set. We trained one model so that we can have an output of any of those combinations. And here is the full scheme of the study. So we have MRE and MRI, and we have this dense unit that we have already discussed and published in scientific reports. And here are the examples of the segmentations that we have achieved using this automatic segmentation. And this is submitted already to scientific report this year. As you can see from the results, both MIMs, so individual models, and unified models achieved very good results. But if we take a look at some graphs, so always IMs, which is individual models, perform better in terms of DICE score in both central zone, peripheral zone, and prostate gland. If we talk about Hausdorff distance, we can see also that IM was better. So here, the lower the value, the better. So here was better. IM was always better than UM, but both of them are decent and they can be used for quantification. If we take a look also at some numbers, we can see that among the MRE and among MRI, both M magnitude and T2 were better at segmenting the prostate and the zones of the prostate because they contain the most anatomical information that are usually useful for segmentation. And if we take a look at some quantification examples, so we took like a quantification analysis of those areas that they were predicted and the ground truth. So here are the areas that the ground truth, here are the areas or the quantification analysis of the areas under predicted masks. And you can see in calculating the t-test that there is no significant difference in between predicted and ground truth masks. So the predicted mask can be already used in a quantification or automatic quantification and analysis of the MRE images. If we talk about future vision, where to go from here, we can see that automatic segmentation is a very robust and powerful tool and time consuming. The radiologist will take almost 12 minutes to segment the 3D volume, while the network can do it in like half a minute or even quarter a minute. We can do some sort of analysis on different areas of the prostate that they were automatically highlighted. We can do some explainability. Once we have the classification on the whole volume, we can design an explainability and we can see where the decision were coming from. We can design a tool also to localize and maybe give us the Gleason score or the estimated Gleason score of the lesion. We can use this localization methods for taking out the biopsy, so just a targeted biopsy, so that we can have the biopsy taken at the right place, not just like blindly taking it from any other places. And also, once we have these histological specimen, we can also segment or classify different type of cells inside these histological specimen. And as you can see here, also we can analyze the whole specimen by taking patches, and we can quantify the Gleason pattern inside each, and then we assign the grade, the final grade, to the whole slice maybe, or the measure of the slice, or so on. I know it's too much information, but let's say let's just conclude something and summarize everything. So project number 1, we have high performance value of AUC, area under the curve, which is comparable to the human reader. We found out that K-trans contains the tumor characteristic. It was the most beneficial for our study. We designed compact neural network that can be used to process 3D images directly. And for project number 3, we can say that prostate cancer versus PPH, we have stiffer tissue properties in prostate cancer. We have reduced water diffusion. We have increased tissue fluidity in comparison to this to the PPH. This correlates to the known histological features, including increased cell density and protein accumulation. Now, if we conclude something from project number 2, we have designed a fully automatic segmentation tool. Segmentation tool of 3D volume could be in seconds. It's a very compact and dense layer with efficient parameters, high segmentation accuracy, and no significant effect of loss functions that we have found, and also the final conclusion that our method outperforms other state-of-the-art methods. From project number 4, almost similar conclusion. So it's very fully automatic segmentation tool, segmentation in 3D volume in seconds. It deals with MRE and MRI maps like on its own. You don't have to specify anything. High segmentation accuracy, of course, and can be used for type of quantitative analysis without any significant loss of information. And if I want to conclude something from my PhD, so I have done many things, many projects in my PhD, including publications and conferences. So publications, we have published already 5 publications. One of them is still in under revision, and the rest are published. 3 of them I'm the first author, and 2 of them I am one of the authors. And in terms of conferences, we have participated in many conferences, in ISMRM twice, in MIDL, in IECR, and SCCT. With that, I would like to thank you all for your attention, and I hope you are convinced that I have done something useful during my PhD, and if there is any question, I would be happy to answer any type of questions that you like.